recording here. All right. So, yeah, I don't know why Tuesday, Thursday classes for me, it's like we never meet. I know we meet for 4 hours a week still, but it's like I won't see you until Tuesday now. So weird. But anyways, I'm not complaining. I'm just saying. All right, so it'll be your job to remember everything we did this week. No, I like to start with a little bit of review. Of course, we didn't do a lot last day, but most importantly, I see 3 people have managed to sign up for WebAssign, so good job. It should be working now, so you should be able to sign up for WebAssign now. I should say register instead. You were always able to sign up. You should be able to register for our WebAssign course now. So make sure you do that. And I think, I don't know if there was something to fix, or they didn't really tell me. I heard from Wendy first saying, oh, I'm in. So I let them know that it was working. And they kind of said, oh, well, I sent it to my supervisor, so who knows? Anyways, technology, right? Okay, so let's see here. Anything else that I wanted to... Oh, I gotta write this stuff down for myself. I need to adjust the due dates on WebAssign. Don't worry, nothing's gonna be due until Friday next week, but I need to adjust some due dates in WebAssign. Okay. Let's say the getting started and 1.1 will be due next Friday. Getting started and 1.1 will be due. That is January 22nd at 11:59 p.m. Of course, that's your time. I'm just dealing in your time, of course. Nothing else would make sense. Oh, my dog's mad at something. Shh. Shh. What a bad dog. No, she's gone blind kind of recently, and so that's sad. But now she just barks whenever she wants anything. She's like, hey, where is everyone? So I think that's what's going on. She'll just stand in a room and go. So anyways, all right. So we'll do a little bit of review, right? We kind of talked about, oops. I was gonna write rules, but for review, right, we talked about, I'm trying to read through my different types of numbers, sets of numbers, right? So most importantly, we're gonna be referring to integers, which are just whole numbers from negative infinity to positive infinity, and then the set of real numbers, which is any number, including, decimals, non-repeating decimals, which we call irrational numbers, right? And so we talked about integers, real numbers, and irrational numbers. Right? So we just kind of cleared those up and put them into their own little categories, right? Of course, integers and irrational numbers are all part of the real number system, so they're kind of baked into each other. Then we talked about the properties of real numbers, right? A plus B is the same as B plus A, right? We just established those rules that we have coming into this course, right? And so we talked about properties of real numbers. Oops. Things like A plus B is the same as B plus A, right? Same goes for multiplication. A times B is the same as B times A. And you can always test these things in your mind. Just let A be some number, say 2, and B be some number, say 3, right? Something easy to think about. 2 plus 3 is the same as 3 plus 2, right? I'll only do the addition side, and then same goes for multiplication, but brackets don't do anything if all you're doing is adding, right? A plus B in brackets plus C tells us, okay, well, we have to deal with the brackets first. So I have to do A plus B, and then I have to add C, right? And so, but that's going to be the same as A plus bracket B plus C, right? So it doesn't matter. And also A times B plus C, right? This is the only one that's kind of, that I see people aren't as strong in. This A kind of gets multiplied on both of these terms, or each of these terms, and you can have more than 2 terms in there, and it becomes AB plus AC. It doesn't matter if the A is on the left or on the right, it has to get multiplied inside to break up those brackets. And then we did some examples there, and then I think that's where we ended. Here I'll make a note. Same goes for multiplication. All right, these rules go for multiplication as well. Okay, so that's where we ended our review. So I'll do a little kind of squiggly thing and review. And I'm usually really bad at indicating when an example is over and the notes start again, but I'll try to use that little squiggly thing just to kind of break up the writing. But I'm really good at forgetting to do that. So we'll see how I do. But there, so that's the end of our review. And let's go back to those notes. And I posted, we'll see how far we get today. We should get into 1.2. I posted the notes for 1.2 as well with the solutions. So you've got the weekend to kind of go through that. And then I've budgeted all of next week for section 1.3. It's a big section, so and it's an important section, so it takes some time, but we've got time. All right, so oh yeah, so we essentially got through the first page, and then we did these examples last day, or some of them, right? And then I posted the solutions. So definitely for this first section, make sure you're able to do all of these problems. What you'll find in section 1.2 is There's a lot of problems. I've given you a lot of practice problems. You don't have to go through, well, you don't have to do anything, but just kind of pick and choose some, maybe some in the beginning, some in the middle, some in the end. They typically go in increasing level of difficulty. So we didn't talk about negatives yet. I flipped through the notes earlier, so I know that. Although we did an example with negatives, and I do kind of assume that you have dealt with negatives. But there's kind of secret properties of negatives that we should establish. So a negative number is really just the positive version times -1, right? And so you can always pull out a -1 from a negative number, right? And then make it positive. If you take the negative of a negative, right, then it becomes positive. Okay, so here, let's just kind of make some notes as we go here. So 1, we can always extract -1 from a negative. The second one says the negative of a negative makes a positive. The negative of a negative makes a positive. And I feel like we already used that property, right? When we brought in that negative inside the brackets. Have to go back, but anyways, we'll do more examples, so no worries. The negative, it doesn't matter which term has a negative value. If you're multiplying, it'll get pulled out to the outside if you need to. In multiplication, one negative value I want to say it can get pulled outside or can be factored out to the outside, right? The fourth point says that a negative times a negative, so a negative a times negative b is just a times b, because a negative times a negative is a positive, right? That's the same as point number 2, right? It's just a little bit more elaborate. So here, if you have -1, well, -1 times 1 is just -1, right? So here you've got -1 times -a making positive a, and then here you're just replacing that -1 with -a times -b, and then you get a positive. So a negative times a negative makes a positive. Same as 2. Negative times a negative, oops, did the times symbol and wrote times a negative equals a positive. Hopefully you guys are okay with a little bit of shorthand here. The fifth one says that if you've got a negative and you have to bring it inside, remember, just think of this negative as -1, right, on the outside that you're multiplying inside. So to expand this thing, you'd have to have -1 times a plus -1 times b, right? And so here, negative a plus b, right, just to do a little bit of work here, is the same as -1 times a plus b, right? And that's from here. That's from property number 1. Okay. So then now we're back to just properties of real numbers, right? To expand this inside, I have to multiply it onto both terms. So now I get -1 times A plus -1 times B, right? And this is the property of real numbers. And then finally, right here, this is property number 1 again, -1 times A. -1 times A is just -A. So we skip these steps, but it can be really helpful to know where all this stuff came from, right? And just kind of convince yourself that, okay, these are just rules that we need to follow. And so here we go. -A, and then technically plus -B, but I'm just going to make it minus B. Right? And that's property number 1 again. Okay. So one thing, right, I'm kind of a stickler for is whenever possible, you should be stacking your equal signs. I didn't do a beautiful job here, but I will always try to stack my equal signs, and it'll hurt a lot if if I can't. I had a page break here, so sometimes I would kind of write things improperly. You'll see. I'll confess right away because it bothers me more than you. But just really try to get in the habit of just stacking your equal signs. And if nothing is changing on one side, you can just keep it and then just keep it empty, and it just makes it easier to read. Right? And then the side that's changing, you can change all the way along. Math rules. Well, I guess it does too, but I meant like rule book. Math rules. Oh, it's fair. So then property number 6, right? If I've got a negative inside here, that's the only thing that's changing. Then let's just look at how this property comes about, right? And we can do the same thing. The only thing that's different from 5 is that we've got A minus B in here, right? And so now we're going to have -1 times -B. -1 times -B by property 2 is just going to be B, right? And so so let's see how property 6 behaves. We've got, oops, -A minus B. Don't worry. You don't have to stack all these equal signs. They just happen to take up the same amount of space. After my stack your equal signs rant. Okay, so what I'm going to do is I'm going to apply this property that we just established. Hey, I think I need to disable so I got this new pencil, and I guess if you double tap it somewhere on this line, it'll switch to the eraser. It's already backfired a few times, so I should probably switch it off. Okay, so I'm going to apply the property that we just established up here, and so I'm going to not skip a few steps. This is how we would do it. But so what I have is I have -A, and then minus B. And that's applying property number 5 that we just established. Right? Because property number 5 says, okay, you're allowed to bring this negative onto each of the terms, but in this case, right, we're subtracting instead of adding, so it changes some things. So this becomes -A plus B, right? -B by property 2 becomes B. what we do to kind of clean this up now, you would be done here, right? But if you notice here, they've got b minus a, right? And you can try it with some numbers. Let a be 2, for example. Negative 2 plus 3, right? Negative 2 plus 3 is going to be 1, right? And then, so if I write it as b minus a, 3 minus 2 is also 1, right? And so here, this is kind of a trick that we use to clean up. If there's a negative just kind of floating around here, then we just kind of switcheroo, and that's just something to be aware of, right? We can rewrite to eliminate the negative. I say eliminate because you're not really eliminating. This is b plus negative a, right? But you don't have to deal with this negative out front, right? Which could get confusing later on. Is it negative? Is it all negative or what? So sometimes we'll do that. So just be aware of that. Okay. But these two last lines are equivalent. So just be aware. Okie dokie. Let's see if I had any examples. No, we moved right on to fractions, so that's okay. Let's talk about fractions then. We are going to deal with so many fractions, it's crazy. So we need to be really, really well versed in laws of fractions. Okay, and so maybe I'll make a note before I copy that in. We will work with a lot of fractions. So we need to, let's say, to be fluent in fractions. We need to be fluent in the laws of fractions. So I'm going to bring that in. We can talk about them. Make it nice and big here. Okay. So the funny thing about fractions is, I would say multiplying and dividing fractions, these first two, are probably the easiest, especially multiplying fractions. Multiplying fractions, all you do is you just multiply across, right? So you've got a over b times c over d, you just smush them together, right? So multiplying fractions is the easiest thing to do. You just multiply across, and then you've got this one combined fraction. To divide fractions, now let's have a look at, I'll just make notes as we go here. One, to multiply fractions, and I will kind of parrot, the description over here, but sometimes it's nice to just see things multiple times. So to multiply fractions, but I'll use my own terminal, we smush the numerators and denominators together. Smush is multiply. We smush, so multiply. Don't worry, that's not a term I'll be using a lot, but just for the visual, I think it's really useful. So to multiply fractions, we multiply the numerators and the denominators. Okay. So that's all fine. Okay. For example, if you have 1/2 times 4/5, right? Who knows? It's going to be 1 times 4 over 2 times 5. We'll talk more about simplifying this, right, later. But for now, right, I'm just going to leave it as this. And remember last day we talked about exact answers and approximate answers, right? So if you do 4/10 on your, let's see here. Now I can't remember what it becomes, but 4, oops, clear all. 4 divided by 10 is 0.4. That's still an exact answer because there's no repeating decimals. But to simplify it, right, would be 2/5 because you've extracted a common factor of 2, but we'll deal with that later. Right. So for an exact answer, 4/10, that's good enough. Okay. So multiplying, easy. Division, so now, right, I actually don't like this division symbol. It saves a lot of space, right? But what we've actually got is A over B over C over D, right? So you've got a fraction over a fraction. And so what you have to do is you can actually, well, what you do is you flip the denominator and you multiply them, okay? So I think some people say flip and kiss, flip and multiply is a little bit boring, right? But if you've got a fraction over a fraction, and I don't know how many times in a term I do this because I have to remind myself how I have to flip it and multiply. Okay, so just kind of get in the habit of using your fingers and just kind of, okay, I have to flip and multiply, and that's how I do it, right? So to divide fractions, we flip and multiply. So for example, and you know what, I'm going to scoot this down to the next page. So if I've got, let's say, I'll use the same fractions, how about, even though I just pulled them out of thin air. 1/2 divided by 4 divided by 5, okay? Notice that what I'm doing is I use smaller kind of divisor lines, right? And then I've got this big one just to remind myself visually what's going on here, right? And so I find it's really useful to just kind of have a large divisor line just so I can see what's going on, okay? And so now what I have to do, so I've got the 1 and the 2 here, and then I've got over 4 and the 5 here. So then what I do is I kind of attach them to my fingers, and then I have to flip and multiply. So this becomes, oops, this becomes 1/2 times, and then the 4/5 flips 5/4, right? So you flip this and multiply. Flip and multiply. Okay. And we're going to do this a lot. So we need to really make sure that we've got it under control. So now, well, now I'm just back to multiplying fractions, right? And so I can just smush them together. 1 times 5 is 5. Over 2 times 4 is 8. 5/8. And I'll leave that in exact form. Okay, so dividing fractions is pretty fun. Just as long as you kind of remember that motion, so the top just holds steady and then the bottom flips and multiplies on. Okay. Oops. If we're adding fractions, we need to make sure that we have a common denominator. So remember, the denominator is on the bottom, right? And so we need to make sure that the denominator for each of the fractions is the same. If they're not, so I will skip down to point number 4 immediately, right? If they're not the same, B is not the same as D, what you have to do is you have to find a common denominator, right? And so I'll just kind of combine points 3 and 4 together here. Three and 4. To add fractions, to add 2 fractions, I guess it's 2 or more. I should be proper here. 2 or more. We're going to stick to 2 for a good long while, but to add 2 or more fractions, we need a common denominator. So remember, we went through that terminology last day, right? We've got a fraction, and I'll remind you here, right? Kind of assumed that you are okay with it, but a fraction is a numerator over a denominator. Until that's ingrained, maybe have that on a like a quick reference sheet somewhere, right? The numerator is on top, the denominator is on the bottom. So we need a common denominator. Okay. If we don't have a common denominator, we need to force a common denominator. If we don't have a common denominator, we need to force it. Okay, and I'll show you what I mean by that. First things first. If I do 3 over 4 plus 2 over 4, here I've got a common denominator. Common denominator of 4. Okay. So what I do is that becomes the common denominator of my combined fraction. All right, so I use that as my new denominator. So here I've got over 4. And then I can just add the numerators, 3 plus 2. 5 over 4. Okay. So here, this becomes the new denominator, and then I just add across. Add across. Okay. So what if we don't have the same denominator, right? How do we force this thing? And there are fancy ways of doing it, but I usually just use this kind of force it through method, and it works every time, and that's why I stick with it. It works, well, it works every time, but it's not that much uglier than doing fancy methods, so I'm just going to stick with this one. I'll show you what I mean here. So if we have 3 over, I don't know, 3 over 7 plus 2 over, I don't know why I'm hesitating, 2 over 3, let's say. Okay. Here, if I'm adding these, right, so you always need to have a look. Okay, as soon as you're dealing with fractions, then you need to think, okay, well, hold up. Am I multiplying? Great, then I can just smush them together. If I'm adding, you have to say, okay, well, then I need a common denominator. So here, then we look, 7 and 3, they're not the same. So need a common denominator. Okay, so what I'm gonna do is, in my mind, I'm just gonna say, well, my common denominator is gonna be this times this. And it can get huge and you can simplify it in different ways, but this will always work. So there's no shame in doing it. So 7 times 3 is my common denominator, right? It's maybe not my lowest common denominator or my least common denominator, but it is a common denominator, so it will work. Okay. The easiest common denominator, is 7 times 3, which is 21. Right? So what I'm going to do is I'm going to have 21. But what that means is on this one here, I need to have 7 times 3. And on this one here, I have to have 7 times 3. So this first term, I need to multiply by 3 in the denominator. And the second term, I need to multiply by 7 in the denominator. But I'm not allowed to just multiply by stuff willy-nilly. But one trick that we use a lot is we multiply by 1. So we pick a convenient value of 1. Now let me just, 3 over 7 plus 2 over 3. Need to multiply by 3. And here we need to multiply by 7. Okay, so what I'm going to do is I can't just multiply the denominator by 7, but I need a 7 in the denominator. So what I can do is I'll just say kind of recall, multiplying by 1 does not change the value. Multiplying by 1 does not change the value. But also, if I do something like 3 over 3 is 1, and 7 over 7 is 1, right? So what we can do is we can pick convenient values of 1 to multiply by. Okay? And I'm spending a lot of time on this because it's probably the part that people struggle with the most. So I want to get it hopefully really clear. And if it's not clear after today, then you will need to work on it until you have that aha moment. Okay, so what we do, and I should make these not look like negatives. There, little arrows maybe. So then a common trick we use, is to multiply values by convenient values of 1. By convenient values of 1. So for example, what we have here is 3 over 7 plus, I think it was 2 over 3, yeah. So what I do is, especially in the beginning, I'll just indicate it with a different color, right? So now I've got here, oops, I've got times 3 over 3 and times, oops, 7 over 7. Okay. 3 over 7 times 1, right? Plus 2 over 3 times 1. Okay. So that's how we force that common denominator. Okay. Now here, we're just individually, we're multiplying fractions, which is easy to do, right? And so now, multiplying fractions. Okay. So we can do that individually, right? We've got, so this becomes 3 times 3 is 9. And you are more than welcome to use your calculator. What you'll find is I am really, really bad at doing math in my head. Even simple multiplication, I don't know, for some reason it just, I used to be really good at it until I did a math degree. Then it's all gone. But anyways, so, and I've come to terms with it. It's okay. I use my calculator for everything. So 3 times 3 is 9, and 7 times 3, now I've got that common denominator of 21, right? Because 7 times 3 is the same as 3 times 7. By the, what's it called? The commutative properties. See, we never use the names, but we've talked about the properties. So plus 2 times 7 is 14 over 3 times 7 is 21. So now we have a common denominator. Woohoo! That's great. So now 9 plus 14, gonna go with 23, but I better check. So now, right, going back to how we add fractions with a common denominator, well, we use the common denominator as our new denominator, and then we just add across. So 9 plus 14 is 23 over 21. And I'm going to leave it in exact form, right? If you write the decimal, that's an approximation. So you don't want to do that unless I ask for a decimal approximation. Okay. Good. So that's probably the worst part of dealing with fractions, is adding fractions that don't have a common denominator. But as long as you remember the trick of you multiply by a convenient value of 1, and that's going to come up time and time again. So we multiply by 1 because it doesn't change anything, right? We don't want to change anything. But we kind of manipulate things until they look like what we want, right? So a common denominator in this case. Okay, so that's property 3 and 4. Okay. With variables, it would look like this, right? And you can kind of work through the variables on your own, but for now, I'm just going to leave it. Okay. Property 5 just says, okay, if you're, oh, and same goes for subtracting fractions, right? You still have to have a common denominator. In fact, I'm going to just sneak it in here, to add or subtract excuse me. So the common denominator bit goes for adding or subtracting. But remember, subtracting is just a special case of addition, right? You're adding a negative value. So that's why they're the same and kind of under the radar here. Property 5 says that if you have some sort of common factor, right? So if you have A times C over B times C, and you're able to factor out a common C in this case, right, then you're allowed to cancel it. This one's a little bit sneaky because people want to cancel from the denominator, but you have to wait until you have a common factor in the numerator. And I'll bring it up when it is kind of more relevant, right? But in order to cancel, so this is property 5. In order to cancel from the denominator, we need to have extracted that common factor from all of the numerator. We need to have extracted that common factor, common this, common that, common factor from the numerator, sorry. Okay. I'll do an example, even though we haven't talked about factoring yet, but we will, so why not, right? You probably have some idea of what factoring is. Factoring is when you break up a number into multiples of itself, right? So 14 you can rewrite as 2 times 7. That would be factoring. In fact, let's use it. So here, if you've got 14 plus 10 divided by 2, okay, this is kind of a Mickey Mouse example, but it's okay, right? In order to cancel this 2, right, I need to cancel 2 from 14 as well as 10, right? So whether you think about it that way, or if you kind of really show all your work, then you would extract a common factor of 2, right? So we would need to cancel, a multiple of 2 from each term, right? And so what you have is you can rewrite this as 2 times 7 plus 2 times 5 divided by 2, okay? Just to highlight that, hey, yeah, I do have a 2 to cancel from each of these terms, and now I can go ahead and cancel, all right? So you can rewrite this as 2 times 7 plus 5 divided by 2. And like I said, we haven't talked about factoring explicitly. We will talk about it. It hasn't come up yet, but this should be okay. So now that I've got this 2 on the outside, now I can cancel here and here. And so now I'm just left with 7 plus 5. 12. Good. Okay. So that's kind of a Mickey Mouse example, but it's good to know what's going on here. And what's that last property, I wonder? Okay, so if, whoop, it's catching up here. if you have a fraction set equal to a fraction, what you can do is you can cross multiply things to get them on the same playing field. I always like to think about them as, kind of the same field. So here, property 6. If a fraction equals a fraction, we cross multiply to get all the terms on the same line, right? Or to move all the terms to the numerator, I should say. To move all the terms to the numerator. So if I have 4 over 3 is equal to, let's say, I might have to introduce I'll do it without variables for now. Usually we have something like X or A on some of these terms, but for now I'll just do this. So what we do is, okay, I can multiply this guy over here, and I can multiply this guy over here. So this is what we mean by cross multiply. So this becomes 4 times 2 is 1 times 3. So 8 equals 3, which is not true. So they're not equal to each other, but like I said, usually we're solving for a variable. We are usually solving for a variable. Such as X, right? Which makes sense, right? 4 over 3 is not equal to 1/2, right? And so here I'll put a little question mark on top. I shouldn't say two things are equal when they aren't, right? I gotta be careful. So say, are they equal to each other? And the easiest way to check that, if you don't have a calculator, is to cross multiply and say, well, 8 does not equal 3, so no. Let's see if I can nab some problems. Did I put any good problems here? I did, not of that, but that's okay. Because we're not solving for variables quite yet. So we'll parking lot that for a little bit. Just work with some fractions. Okay, so let's do, you know what? Let's do 30b, definitely. And then I also want to do 32b with you guys. So 30b is 1 plus 5 over 8 minus 1 over 6. So here we're dealing with 3 terms. That's fine. We can do that. The same rules apply, right? We said 2 or more. We need to have a common denominator, right? Because we're adding and subtracting. Subtracting is just a special case of adding. And so here we need to have a common denominator. Need to find a common denominator. Right. One thing that we're going to use a lot of is if you have an integer like this, so 1, right, a whole number, that's not a fraction, but you can always rewrite a number as a fraction if you do 1 over 1, right? we can always rewrite an integer, right? Using our terminology already, right? An integer is a whole number, whether it's negative or positive. We can always rewrite an integer as a fraction by putting it over 1. Right? So 1 is the same as 1 over 1, or 4 is the same as 4 over 1, right? We know that kind of math, right? 4 over 1, that's 4, right? And so sometimes we need to manipulate it and make it a little bit uglier before things get better, right? So putting it over 1 just makes it a fraction, and now it's easier to deal with. Right? So what we can do is we can rewrite, so 1 plus 5 over 8 minus 1 over 6, I'm just rewriting it here, is the same as 1, and I'll use a different color, over 1 for all the things that I'm, plus 5 over 8 minus 1 over 6. My common denominator is just going to be 1 times 8 times 6, right? So I just multiply all my terms together in the denominator, right? And that'll be my common denominator. Okay. So 1 times 8 times 6, so this term here has to get multiplied by 8 times 6. The 8 has to be multiplied by 1 and 6. The 6 has to be multiplied by 1 and 8. So we do the same thing. It's a little bit more work because we've got 3 terms instead of just 2, right? But what we need to do is our common denominator, just make a note here, common denominator, I'll just write denom, is 1 times 8 times 6. And I'm not going to simplify that, right? I'm not going to do 8 times 6. I'm just going to keep it as 1 times 8 times 6 until I'm ready to multiply. I'll show you what I mean. So this is going to be 1 over 1, and then here times, right? I've got the 1, now I need the 8 and the 6. So times 8 over 8 times 6 over 6. Okay. Plus 5 over 8 times, I'll do the 1 over 1, you don't have to, right? 1 over 1 is just 1, anything times 1 is just itself, right? But 1 over 1 times 6 over 6, minus 1 over 6 times 1 over 1 times 8 over 8, right? So you do whichever one is missing, right? But each of these terms has to have 1 times 8 times 6, and order doesn't matter for multiplication, right? 8 times 1 times 6, 6 times 1 times 8, they're all going to be equal to the same thing. So now, right, here, now I'm ready to multiply and simplify this thing, right? So 1 times 8 times 6, 1 times 8 times 6 is 48, no surprise. Okay, so what I have is 1 times 8 times 6 over 1 times 8 times 6. That's good, right? 48 over 48 should be 1, right? The whole goal is that we're not changing anything. So 48 over 48 checks out. So I get 48 over 48 plus 5 times 6 is 30 over 48 minus 1 times 1 times 8 is 8 over 48. So now I've got my common denominator of 48. So now I just apply my my addition and subtraction as I move across here. So 48 plus 30 minus 8 puts me at 70 divided by 48. Good. Okay. So once you're over that that hump of finding the common denominator and figuring out what it is, and that's why I just like to just multiply things across. Like I said, there are fancier ways to do it, and the textbook will go through and show you fancier ways, but for me, no, I just multiply across, and that's my common denominator, even though it could be a little bit cleaner, but that's okay. 48 still works. Okay. So what was the next? I wanted to do 32b. 32b. And I keep 2 over 5 plus 1/2. 2 over 5 plus 1/2, all divided by 1 over 10 plus 3 over 15. Like that. Okay. So to deal with this, right, I'm adding two fractions in the numerator and in the denominator. So I'm going to work those individually, but kind of alongside each other, right? And then I'm going to end up with a fraction over a fraction, which is two fractions divided. And so then I can flip and multiply. But first I need to simplify. Simplify the numerator and denominator into single fractions. So this becomes, and I'm going to put my equal sign over here this time because I wrote on the other side. So now, right, going a little bit faster here, for my common denominator, I'm going to have 5 times 2, which means I need to have times 2 on this term and times 5 on this term, right? And so what I'm going to do, I'll still show it with different colors. And I tend to do that throughout the course, right? Just to highlight what I'm doing. So 2 over 5 times 2 over 2, right? Convenient value of 1 is what we multiply by. Plus 1/2 times 5 over 5. Okay. Then I do the same thing in the denominator here, 1 over 10. So now I've got 10 times 15 as my common denominator. It's not my lowest common denominator. That's okay, right? 10 times 5, that's what I'm going to use. So I've got 1 over 10 times 15 over 15 plus 3 over 15, oops, times 10 over 10, right? Forcing common denominators. Now, I definitely do not need the same common denominator in the numerator as in the denominator, because remember, once we flip and multiply, multiplication, you just multiply across, right? So you don't need to keep that in mind. That would be way too much work. So what we have, right? We're multiplying, so 2 times 2 over 5 times 2 plus 1 times 5 over 2 times 5. So I've got 4 over 10 plus 5 over 10. Makes sense, right? 5 over 10 is 1/2, right? If you think about it. Same thing with 4 over 10 is 2 over 5, right? I've just boosted them so that they have the same common denominator. Over 15 over 150, right? 10 times 15, just making sure, yep. 3 times 10 is 30. over 150. Okay. Now I can add these, right? Because they have common denominators. So I get 4 times 5 is 9 over 10. Divided by 15 plus 30 is 45 over 150. Right? And just kind of emphasize that this divisor line is a little bit larger than the other two. I didn't do a very good job, but I guess I can extend it just to show that, hey, I've got a fraction over a fraction. Now, right, I flip the denominator, right? So I've got a fraction over a fraction. I flip the denominator and I multiply, right? So what I do is this 9 over 10 stays the same times, and then I've got 150 over 45. 150 times 9, because now I'm just multiplying fractions, so you just smush them together. 9 times 150 is, and I just did it here, 1350 over 450. Okay, I would be happy with that as your answer. I suspect that it simplifies quite a bit, so I'm going to use the Desmos calculator to see, what they say. 1350 over 450. Three. Womp womp. Right, but if you left it as 1350 over 450, I would be happy with that. Right, if you got to that point, which is 3 from calculator. Not something that I would expect you to do. Okay. Although you could apply that cancellation property if you wanted to get fancy, right? You can extract a 9 from 45 and you can extract a 10 from 150, but I wouldn't bother. Okay, great. Fractions. So like I said, we're going to deal with a lot of fractions, and we need to be fluent in fractions. So make sure that you're able to do all those problems, because I didn't give you very many here. So make sure that you're able to do all those, and then we'll pick up more as we go. Okay. Before we head into sets and intervals, I think what we should do, let's do a 5-minute break just to kind of break up the morning. Also, I need to blow my nose again, so. But let's take a 5-minute break, and we'll be back in 5 minutes. How about that? Yeah, coffee time. Yeah, again. All right, so we've already talked about sets of real numbers, sets of integers. So, but now we're going to take it down a notch and just talk about, okay, well, what if I just have a set of numbers and I just list the numbers? What if the set is so small that I can just list the numbers and the elements inside the sets? So a set is a collection of elements, okay? And usually we use S to denote a set, or A, B, C. We use capital letters for some reason, often, and or always rather, for sets. And there are a couple of ways that we can denote sets. So the fanciest, I would say the fanciest way to denote a set is through set builder notation. So let's see here. I'll put it on a fresh page here. So for sets and intervals. Okay. A set of numbers can have an infinite number of elements, such as the set of real numbers, right? So we talked about the set of real numbers. That's every number from negative infinity to positive infinity. And so you'd have an infinite number of elements, such as the set of real numbers. Right, which, just as a reminder, we use that fancy script R, right? So a capital R with a double back. Okay. Or, I guess I should end that, not have a run-on sentence. Or, sometimes we're able to list the elements. Or sometimes we can list the elements. Okay. Sets are contained in curly brackets. Sets are contained in curly brackets. And I'll add, because I said it, and denoted using capital letters. And denoted using capital letters. So for example, A is the set of the numbers 1, 2, 3, 4. Okay. Right? So here we've got 4 elements, 1, 2, 3, and 4. Those are the only elements in A. Okay. We can also have B, which is the set of numbers 2, 4, 6, 8, 10, 12. Okay. So if we have 2 sets, we can talk about the intersection of those sets, so the overlap, or the union, which is just everything in the overlap as well as the 2 individual sets. Okay, so if given 2 sets, we can discuss the union, which is just going to be a capital U of the sets, all elements from both sets, or I guess or we can discuss, I'll do the same format, discuss the intersection, which we denote with an upside down U of the sets, which are all the overlapping elements So if you think about the union or the U as if it's an or, and the intersection or this this kind of upside down U as an and, right here. Oops. And then it might help when you're trying to figure out which ones are the overlapping elements and which one you just kind of combine your sets and eliminate any duplicates. Well, you include them, but only once, I should say. So for example, here, if we have our sets A is 1, 2, 3, 4, and B is 2, 4, 6, 8, 10, 12, sorry, I forgot about that one. Then if I take the union, right, A or B, so A union B, A union B is the set of any element that is in either A, oops, I did it again, either A or B, right? So 1, 2 is in there twice, 3, 4 is in there twice, so we just write 1, right? We don't need multiples. And then 6, 8, 10, 12. So this becomes 1, 2, 3, 4, 6, 8, 10, 12. Oh, that's a terrible curly bracket. I'll try again. Although what I find is my left curly bracket is always really nice, and then my right curly bracket is just kind of like, ugh. It's always been that way. But see how you do. All right, so A intersection B, so A and B. Okay, so the elements have to be in both A and B. And we just highlighted that 2 is in both A and B, and 4 is in both A and B, and those are the only 2 elements. So A intersection B, or A and B, is 2 and 4. What if I add a third set here, right? What if I let C be the set, and you can add it anywhere, but I just wanted to have them together. I should have introduced it earlier, but that's okay. Is the set of 9 and 10. It can have any number of elements. How about, what if I want A or C, right? A or C is 1, 2, 3, 4, 9, 10. Okay. So A or C is 1, 2, 3, 4, 9, 10. Right? The elements just have to be in either set in order to qualify. However, A and C, well, I need to find an element that's in both of these sets. Well, they share no elements, right? 1, 2, 3, 4, no elements in common with 9 and 10. So what we do is we use the empty set. Okay? And the empty set looks like this. And I should clean it up. Right. This is the empty set has no elements. Okay. It is a set on its own, but we're not going to go into set theory or anything, but the empty set is just to denote nothing in common here, right? And that can definitely happen, right? If there's no overlap, then that's all right. It's the empty set. Okay. So that's kind of what we need from sets, right, before we move into intervals. But let me just go through, because I had these notes are more comprehensive, right? Okie dokie. So we use this kind of kind of a funny looking E, right? To denote is in the set. We use E as shorthand. Now, of course, it's not an E, it's kind of a C with a line in it, as shorthand for is in the set, right? So for example, 4 is in the set A, right? A has the element of 4, so 4 is in the set A. How about 8? 8 is in the set B, but it's not in the set A or C. So what we can do is we can do something like 8 is not in the set A. Right? Not in the set. Right? So we can use that to kind of exclude elements from a set, right? Or to show that elements are excluded. Right? So just kind of walking you through some of this math notation. Okay. So we talked about the is in the set, and so we can have set builder notation, right? Where we use the curly brackets, right? Again, for sets, we use curly brackets. And then we read X such that, and then we've got the conditions on the set after that vertical line. So let's see here. We can use set builder notation. Instead of listing all the elements. Means we have to summarize the elements somehow in a clever way. But so here, if we let A, remember A is 1, 2, 3, 4. Okay. Then what we can say is, okay, well, I know that these are integers, right? So 1, 2, 3, 4, they're all whole numbers. So I can summarize them as integers. And I'm limiting my integers because I've got all of them here, 1, 2, 3, 4. I'm limiting my integers to be between 1, including 1, and up to 4, including 4. Or if you want to go to 5, but not including 5, that makes sense too. So there are a couple of ways that we can write it. So here in set builder notation, A, still A that we're talking about, is the set, so curly bracket, the set of X, and I'll write out what I'm saying as I write these, as the set of all X's such that X is an integer and X is between 1, including 1, and 4, including 4. Right. We haven't talked about inequalities, so don't worry about it quite yet. We'll leave inequalities until section 1.8, but we'll introduce them here. But kind of low stakes, right? X is between 1 and 4, including 1 and 4. Right? So X is an integer, is one of the conditions, and then here we've got another condition. So here what we read is A is the set of, so here the set comes from the curly bracket, the set of all x such that, and that's from the curly bar, or sorry, the vertical bar. I don't know why I say curly bar, that makes no sense. Such that, and then the conditions. Right, conditions on the x, right? So x is just any element in the set A that satisfy those conditions. Okay. I'm not going to use set builder notation that much, right? I'll use interval notation, which we'll introduce next, but I won't use set builder notation that often, but it's important to be able to read it. Note, I will not use set builder notation that often, but it is important to be able to read it. It is important to be able to read it. Okay. Okay. So let's go back to our notes, see where we're at. Maybe there's an example in our future. So here we actually just did one like this. So I want to move on to intervals, but make sure that when you work through these on your own, right? I've got the solutions posted on Moodle. So make sure that you're able to kind of go through these and they all make sense, right? So do these on your own, 41 to 44, A and B for both. Oof. Okay, so when we talk about intervals, which we did when we said, okay, x is an integer and x is between 1 and 4 inclusive, right? We can talk about open intervals or closed intervals. And we said, okay, including those endpoints, we use the less than or equal to, and excluding those endpoints, we use just the less than sign. So for intervals, right, if we just go to the next page here, right, an interval is probably easiest to see if you're working on a number line. So an interval is just a stretch from the left-hand side to the right-hand side, and that's important. I don't want to see things like the interval from 4 to 2. That doesn't make sense, right? The interval from 2 to 4 makes sense, right? So you want to be careful. But what we're talking about here is whether the endpoints are included or excluded, right? So if they're included, we use closed dots, so filled in dots, and if they're excluded, so up to that point, so super, super, super close, but not including that point, then we use open dots. Okay, so instead of set builder notation, I will often use interval notation. Which, okay, is just going to be an interval from A to B. So if you have x is less than, so A is less than x is less than B. Okay, so any x is, so whenever you see an x is just kind of a placeholder for any value that you're looking for, it's between A and B. So here then, we've got less than, and I had a heck of a time with inequalities. So these are inequalities. So less than, people always do the alligator, it eats the bigger number. That actually didn't make sense to me because the alligator would be, anyways, I don't know why I had such a hard time with it, but I did. And then it wasn't until I was teaching inequalities that someone was like, oh, you can just make an L on with your left hand, right? So the loser symbol, right? And so what I want you to do is I want you to make the loser symbol and then go A is less than, and then you can just read across, right? If it is an L, then you read it as less than. If it's not an L, it's not less than, it's greater than, right? So that's what's nice about having just two options, is you only need to remember one. So A is less than, X is less than B, right? So less than, but not including the endpoints. So on a number line, you would show that as A and B. Then I guess I should use a different color here. So between A and B, but not including A and B, right? So we use the open dots here to indicate that. Versus if A is less than or equal to X, which is less than or equal to B, then on a number line, right? This is including the endpoints. So if you have a number line from A to B, I'll use that green, then, oops, I do a filled in dot at the endpoints. To show that I'm including those endpoints, right? And I can do a combination of these things, right? And so okay, sorry, I had some stuff pop up on my screen. I got distracted. But anyways, people logging in, logging out. That's okay. So interval notation, instead of having this inequality stuff, right? What we can do is we use brackets instead. So we can use round brackets or square brackets, right? And so in our notation, right, here, use round brackets, and it'll make more sense in just a tiny bit. And if you're including the endpoints, you use square brackets. Use square brackets. And I'll grab an example here. Oh. Jump ahead a little bit because that's how we introduce things. Okay. So we want to express the inequality in interval notation. So interval notation is going to be with the brackets, right? And so here we've got an inequality and we want to make it into an interval, which is just easier to look at. So just as an example, let's have a look at 53. If X is less than or equal to 1, right? So remember, less than or equal to 1, so it includes that endpoint of 1, then I'm going up to and including 1. But from the bottom here, I'm coming from negative infinity. So from negative infinity to 1, so X is less than or equal to 1, I would denote like this. So we always have round brackets around infinity, positive or negative. because infinity is not actually a number, it's an idea. So you can't include infinity because it never ends, right? And so we have to use round brackets. We must use round brackets around plus minus infinity. Okay. So to kind of solidify this idea, let's do 55. If x is between -2 but not including -2, and going up to 1 including 1, this is the same as -2 round bracket up to 1 square bracket. So inclusive of 1 but exclusive of -2, but it's the interval from -2 to 1. So on a number line here, if I have -2, oops, I'll clean that up. -2 and 1, how would I draw this? Well, I would have a filled in dot at 1 and an open dot at -2, and then connect the two, right? So there are a lot of ways that we can indicate the same thing. Okay? A lot of the time, your answers, especially in WebAssign, are going to require interval notation, and so this here is interval notation. Okay? And I think I'll clarify that up here. So because what I said was instead of set builder notation, I will often use interval notation, but then I introduced the inequalities. So here, using round and square brackets. How about that? So give those other ones a go. And also, right, you can convert these intervals into inequalities and move back and forth. But before we go, what I want to do is I want to talk about sets with intervals, right? Because that this is definitely kind of a common test question that I ask. So here, let's kind of end on a high note. So we want to find the indicated set if x, and now we're, like I said, we're reading interval or set builder notation. I'm not going to use it, right? When I give my answer. Okay, so x such that x is greater than or equal to -2, and x such as, so b is x is less than 4, not including 4, and c is x is between -1 and 5, not including -1, but including 5. So what we can do, or what I like to do, is just kind of put these all on the same number line. And you'll need quite a bit of space up above. So, and what we do is you're just going to figure out which tick marks you're going to add on here. So my smallest value here is -2, and then I've got a -1. The spacing is not important. It's just to visualize. So -1, and then 4, and then 5, right? Something like that. So what I'm going to do is I'm going to draw my interval for A, and then my interval for B, and then my interval for C, and see where that puts me. So I'll use different colors here. A, x is greater than or equal to -2. So here I've got from -2 And it just keeps going and going and going and going, which I indicate with an arrow. Okay. And then I've got my set B. B is all my x's that are less than 4, but not including 4. So here, I've got an open dot at 4, and then I keep going and going and going and going. Okay. And then C, from -1 to 5, okay, I've got an open dot at -1 and a closed dot at 5. Okay. Now I can use this number line. So that is a little bit of work before I can go ahead and answer these questions. But once I have it all laid out, it's actually really easy to kind of figure out, okay, B or C, that's any element that's in either, right? And so now I'm just focusing on B, which goes from -infinity to 4, but not including 4. But then C is also in the mix, which includes 4, but doesn't include -1, but -1 is included in B. So here, right, what it's going to become is it's going to be the interval from -infinity all the way up to and including 5. So 45A, B, or C is the interval from -infinity up to 5 and including 5. And let's do B as well, B and C. Now it's just the overlap, right? The overlap starts here at -1, but not including -1. And then it ends here at 4, but not including 4. So it's from -1 to 4, round bracket. And I'm out of time. All right. But I haven't seen any questions, but if you have any questions, let me know. Otherwise, go through those notes. The rest of the notes I posted were almost done 1.1. And then we'll get into 1.2 next week. All right. Thanks, guys. See you Tuesday. B is from -infinity to 4, but not including 4. Does that make sense? Because it's x is less than 4, but all x is less than 4. Oh, do you mean here? So here, okay. So here we're talking about, so what we want to find is B and C, so the overlap. Now the overlap of B and C doesn't start until -1, but not including -1, right? So if you're looking at this and kind of upside down U, then you only look at the overlap. So from -1, not including -1, up until 4, but not including 4. Does that make sense? Awesome. Cool. Thanks, guys.